Let's wait another minute or so. All right, can everyone hear me?
Yeah.
All right. Let's just wait one more minute, give everyone enough time to join. Then we'll get started. Okay, Chris, you ready?
Yes.
Okay. Hi, everyone. Welcome, and thank you for taking out your time to attend this webinar. Today, we'll be talking about the automotive testing for conventional and electric vehicles. Before we jump into the presentation, I would like to go over our agenda. We're going to start with an introduction of our presenter and our panelists. Then we'll move on to the presentation, which will last about 40 minutes, and we'll end it with a short Q&A session, which may last about 10 minutes or a little bit longer. During the presentation, we're not planning to stop to answer any questions, so we highly encourage you to type in your questions in the question box. And we're not planning to take any questions regarding pricing or product quote during the webinar, but you're more than welcome to write us on a separate note, and we'll be gladly to further assist you with any questions you may have. All right, now I would like to introduce our amazing presenter, Chris Schultz. He is our newest product manager, and he comes with an extensive background. Right before joining our team, he was a product manager with RNS, where he was responsible for the Vector Network Analyzer product portfolio. And he also holds a PhD degree in electrical engineering and a master's degree in aerospace engineering from the Georgia Institute of Technology. And today we have our two panelists here who will be helping us during the Q&A session. Our first panelist is Naomichi Miyari. He is our product marketing engineer and has been working for Hioki for 10 years, and he is very knowledgeable. And our second panelist here, Fumiyaki Iyagi, is our research development engineer, and he has been with our company for 10 years also. Now with that said, let's please welcome our presenter, Chris.
Hey, thank you very much, Jennifer. It's a great honor to be here and talk a bit about automotive testing for conventional and electronic vehicles. In these 40 or so minutes, I'm going to talk about a bunch of things, a variety of things. You know, there's a lot of talk about autonomous vehicles, 5G, cell phones, wireless connectivity. Most of the people that talk about this ignore that there is a lot more electronics in automobiles and moving infrastructure than just the wireless connection. Actually, this might be more and more important than the wireless connections. So a bunch of things that I'm going to talk about in the seminar. Can't get into all the glorious details. We do different seminars on specifics. We're going to talk about motors, engines, ECU, the electronic control unit. I'll talk a little bit about interior testing. I will mention some of the aspects of battery testing for electronic vehicles. I'm going to have some specifics about drive tests. You know, drive tests is testing vehicles, excuse me, on the road. That's very different than testing vehicles in a lab. Got some notes on maintenance of vehicles, crash testing, and then the external infrastructure of electronic cars, which is specifically fast charging. a quick overview of the industry. I mean, we all know that the mobility and transportation industry is rapidly changing. That's probably the hottest field to be in right now. I mentioned this already. We have a lot of talk about autonomy, but there is a lot more stuff going on behind the scenes that is much less popular, but from a volume and from a dollar amount, maybe much more important than the wireless infrastructure. There is a tremendous proliferation of sensors in modern vehicles that is not only specific for electric vehicles, but traditional internal combustion engines start having a slew of sensors that all need to be tested, integrated, managed. Entertainment is a big issue. Gas mileage is becoming more and more of an issue, maybe more in other parts of the world, but it is happening in the US too. And then, of course, crashworthiness, right? Human life needs to be protected. Crashworthiness testing has always been high on the priority list. Specific hybrid vehicles, there's a whole new set of tests for drivetrain management. And then power efficiency. Anything that carries a battery, power efficiency becomes increasingly more important. Even more so for electronic vehicles, electric vehicles. Battery management's been becoming one of the major hurdles. We had some reports of batteries going up in flames. That goes through the popular press. By all means, that's something that everybody wants to avoid. That's not good for anybody involved. And then power efficiency, again, if you have full electric vehicle, power efficiency is probably the most important thing, which is directly related to range. And then, of course, charging. So let me talk about motor measurements first. Obviously, the electronic vehicles have electric motors in there. It's not just for the drive, but also for many other applications. Electric motors in modern cars are pretty much anywhere, be it the starter motor or motors for windows, parking brakes. Many of the parking brakes in modern cars are electric these days. One of the big challenges in motor developments is temperature measurements or temperature design. It's nothing's really easy, but it's relatively well established in building motors and calculating and deciding motors. The electrical part of the motors is relatively well established. Doing thermal analysis of motors is a big challenge, and many of the models rely heavily on accurate measurements of the temperature distribution throughout the motor. So a lot of the simulation tools require accurate measurements. Cooling fans are usually done empirical, so you build the motor and then measure how the motor works. Thermal measurements can be very challenging. You need to typically have multiple points where you measure in a motor to get accurate description of the thermal distribution. You need multiple channels to test highly accurate measurements. It's actually very difficult to measure temperature accurately. Usually it is temperature differentials that you are interested in. One instrument that's been very popular is a memory logger, like the LR8450. Comes in two versions, LR450 and LR450-1. That's been used quite a bit for thermal measurements in motors. You can do a lot of things with this memory logger. You can set trigger conditions that makes alarms going off when certain thermal sensors reach a certain temperature. You can log a temperature with a very high temporal resolution, so we can measure up to 10 milliseconds per period or down to 10 milliseconds per period. And a very cool feature of the LR8450 series is that we have variant, the -01 variant, that can use wireless sensors. So you can put your thermal sensors anywhere in the motor, don't need to run cables. The memory logger acquires the data, transfers it via LAN, for example, to a PC. That could be a free software that you're using, and you can do all your data analysis remotely on a computer. Adding a bit more flavor to that now, so I do have my motor right here, and I have a rotary encoder. Rotary encoders are used to measure the speed of the motor and the direction of the motor. So they are very, very important or very critical in correctly analyzing the state of a motor. Typically, rotary encoders have two phases that are 90 degrees out of phase. There's an A phase and a B phase that gets acquired by an instrument. So basically what you have is you have four signals, or if you combine the A phase and the B phase, rising edges, falling edges, you get four type of combinations per bit period. Which means that you start acquiring quite a bit of data pretty rapidly, especially with fast spinning motors. So it's very important to measure the data or to acquire data with a high enough sampling rate. Many of the older memory recorders didn't have that sampling rate. What we do have is, for example, an MR6000, a memory recorder 6000, that can record data up to 50 megasamples per second or up to 100 megasamples per second, depending on the modules that you have in the memory recorder. This gives you enough bandwidth to acquire any minute changes in the speed of the motor, so you can correlate any issues that you have to the specific state of the motor. We can also use a probe to probe the current or the voltage that goes into the motor. So that simple system gives you an easy way of analyzing motors, designing motors, verifying the operation of a motor based on speed and electric footprints. Mentioned already that thermal measurements can be very challenging to do. This is specifically true when you're talking about batteries. Now, batteries are very sensitive to thermal events. If they overheat, the capacity goes down. If they get even hotter, they can catch fire and combust. Again, that's something that you want to avoid by all means. Challenges with batteries that are built in cars is that they're usually built in the cavities of the cars that are very hard to access. So it's usually possible, but very difficult to run cables to each of the batteries. Now, the batteries consist of multiple cells. In an ideal situation, you want to measure the state of each and every cell separately. So you would have to have a lot of cables into your car. That's first of all difficult to install, if it's possible at all. And then of course it adds weight and potential for interference. You pick up a lot of noise when you have a bunch of cables running around in the car, especially when they're close to high performance motors that generate high magnetic fields. So what we do have is a way of connecting thermal sensors wirelessly to instruments like the LR8410. And that's a really cool features. So you basically only need to put your thermal couplers or voltage meters or whatnot in the battery or whatever area you have, connect to the memory logger like an 8410, and acquire the data wirelessly over a long period of time with high accuracy. You can also combine the LR8410 with other instruments, like for example, a power analyzer, PW6001, as shown here. So you get a full overview or full accurate measurements of all the parameters that you have going on in your car without running running a lot of wires through your moving structure. So let's add some more detail to this drivetrain. I started out with talking about the motor and the pulse encoder. Electric vehicles have a lot more, of course. There's typically a battery, obviously. I mentioned the thermal problems of batteries or thermal measurements of batteries in the previous slide. And you do have an inverter that connects the DC voltage of the battery to AC voltage and current in the motor. That's relatively straightforward to do. The next challenge, of course, is that you usually want to correlate any mechanical problems that you might see to the electric drivetrain. That could be vibrations, that could be inconsistency in the torque at the output of the shaft of the motor, and any other possibilities. So correlating the electric parameters of electric vehicles to the mechanical behavior of the car is crucial and is very challenging. You could use multiple instruments, use the strain gauges, acquire data, use the electric data, acquire the data, and then try to correlate the data in post-processing. It's being done, it's a tedious process. What we have built at Hioki is a memory recorder, the MR6000, that allows you to attach strain gauges directly to the instrument. That is attached via a strain unit, the U8969. You can also use vibration measurements through piezoelectric transducers, for example. That we have a U8979 that is specifically built for piezoelectric transducers, has anti-aliasing filters built in. So with one single instrument, with an MR6000, you can acquire all the data you need, all the electric state of your drivetrain, as well as the mechanical state of your drivetrain in one single shot over a long period of time. You can also do analysis on the data. What I'm showing you here on the right-hand side is the signal of the torque transducer and the vibration transducer, the piezo transducer. And you can do a Fourier transform, a fast Fourier transform at the same time that shows you the various vibration of these two mechanical sensors. So in this case, we're showing a Fourier transform of the vibrations, and you clearly see a peak in the 1 kilohertz region. And similarly for the torque, you see the Fourier transform of the torque. And with this footprint, you can really quickly troubleshoot issues and vibrations at the drivetrain and find the root cause of any issues. And one of the real big challenges is when things become dynamic, when you start and stop the motor. These transitions are usually what are very hard to troubleshoot because, well, every time you want to measure it, you need to ramp up your motor or ramp down your motor while acquiring all the other data. Yeah, again, there's a lot of value in having just one instrument, acquiring all the data, and allowing you an analysis on this large touchscreen panel, like I'm showing right here. So I mentioned the strain transducer, the strain unit, the 8969 already. We also do have frequency units, the 8970, that measures the rotational speed of the drivetrain, of the output shaft. And what you can see here on the right-hand side are the various sensors or the various readings that you have. We have the motor power, that's a calculated value. We can calculate the inverter power in the red curve, just like here. And you can overlay it with the mechanical torque measurements. Right here at 1 second, you kind of see the spike in the torque. That's an effect of the ramp up power. Interesting enough, the motor efficiency is pretty much flat over the whole region. To further analyze the data, we allow you to, or we give you the features to do XY plots. So you could, for example, plot rotational speed or torque on the Y-axis and rotational speed on the X-axis. or you could use plot motor power or inverter power as a function of rotation speed directly on the instrument. So very powerful tool in analyzing and designing any of your electric or electromechanic drivetrains for electric vehicles. Now you can drill down into all the details when you have when you start seeing issues. What I'm showing you here in the slide is the same drivetrain again with battery, inverter, motor, torque sensor, pulse encoder, and then of course load. I'm showing you here 3 current sensors after the inverter and 1 current sensor in front of the inverter to give you the power measurements. We also do have voltage measurements or voltage probes on the input and the output of the inverter. So with this information, you get a quick view over the various powers, 3-phase power, RMS power, and then you can drill down into the individual currents or the individual voltages at the motor and analyze the ramp up, ramp down issues, and understand any problems that might happen in the electrical side. And again, you could correlate the same thing to any mechanical issues that ultimately you see when you drive the car. If you want to get down into the detailed evaluation of motors, that's when a tool like the power analyzer, a PW6001, for example, comes in. That's a relatively small unit, again, that hooks up with various current sensors and voltage sensors and measures the electric parameters of your inverter or of your motor. So you can correlate that to the pulse encoder. You can correlate to the state of the drivetrain. You can, of course, hook up torque sensors at the same time. So what this instrument gives you is a very accurate measurement. It's a very high update rate of only 10 milliseconds. It gives you all the critical parameters of your electrical system, including peak torque, peak power, energy conversion efficiency, operating voltage, state of the battery, and many more. So a very powerful tool that helps you go into all the details of your inverter, of your battery, and of your motor in a tremendous amount of detail and with very high accuracy. Now here's one development that we have seen during the last few years. Electric motors have become extremely efficient. That's been driven by solid state power devices. Gallium nitride technology has enabled switching devices up to very high speeds, which has given the industry a huge boost in efficiency. Motors have, electric system have migrated to very low on resistance. So the motor system, the electric motor system has has gone all the way up to efficiencies as high as 98%. And that's pretty amazing. The range of EVs has increased as a result. Trouble with that is that you have 2 things that are working against you from a measurement perspective. Number 1, you need to start measuring at high frequencies. And number 2, you need to measure at very high precision. Right? We have seen a fair amount of customers who measured their highly efficient drive system and came up with efficiencies that were beyond 100%. That, of course, is physically not possible, except, of course, the odd movie on YouTube that gives you free energy. It just doesn't exist. So that's been a challenge for the test and measurement industry. We traced many of these issues back to number 1, high frequencies. So if you look at the right-hand side here, I'm plotting the gain and phase characteristic of current sensors. Now, current sensors are not known to be very high speed. Right? They drop off at higher speeds. So if you look at the blue curve here, that's the gain of one of our current sensors, the CT6904. And that one drops down by about 10 dB at 10 megahertz. So there's a pretty sharp drop. It's very flat up to them. Now, if you look at the phase drops off, or the phase deviates from 0 much earlier than that. And that combination of frequency drop off of current sensor and phase drop of current sensor has gotten wrong measurements when you go to higher switching speeds. Hioki is unique in the sense that we built our own current sensors. So we have full control over the manufacturing process and the characterization of current sensors, which also means that we can compensate for the non-idealness of current sensors. Our instruments, like the power analyzer PW601, is conscious of the current sensors that's attached to it and can compensate for the phase or the phase roll of current sensors. Now that means that if you look at the orange line here, that we have a compensated current sensor, phase compensated current sensor that goes all the way up to 1 megahertz. And that is crucial when you're talking about high switching speeds of modern inverters that are typically GaN biased. We also can do fast Fourier transform in this box. We have an excellent common mode rejection ratio. And a really cool feature of the PW6001 is that you can characterize two motors at the same time. Driving motor, or it could be a generator or a regenerative drive. So you can correlate both at the same time and see the interactions with super high accuracy. And again, we don't have problems with motors that go into the 98% efficiency range. All right, enough about motors. Let's switch gears and talk about engine measurements. So here's an example of an internal combustion engine, or a problem that we've seen a lot in traditional internal combustion engines. There are two problems that, or two effects that are working against each other. So when you want to analyze the spark voltage into a spark plugs, you need a fairly high sample rate. So typically you need about a microsecond per sample, or less than a microsecond per sample, to get enough to analyze the footprint of the spark signal. Now the problem with internal combustion engine is, of course, that there are a tremendous amount of mechanical issues, stress, strain problems, temperature problems. Now these effects are at very different time scales, right? So when you're talking about stress, strain, and temperature, typically you're talking about milliseconds or maybe even seconds of acquisition time. So the problem here is that, yes, you need an instrument that is very fast, that can sample at a very high sample rate, but it can also measure very long record length. For this reason, we built a memory recorder, the MR6000, that has various modules. So you can attach a high-speed analog module, the U8976, that can sample at microseconds per samples, but you can also use record length of up to 5 seconds. So this gives you a system that can measure 200 megasamples per second for up to 5 seconds, and you can acquire effects that live on very different time scales. So electrical effects that are usually at very fast time scales, and mechanical effects that are at low time scales. Again, you do this whole thing, you measure all these effects into just one single instrument, so you don't need to do any post-processing, stitching, alignment of data, and alignment is always a major problem. Various models that we have available, current sensors, strain sensors. I mentioned some of them in some of the previous slides. All right, let's move on to battery testing. I want to talk about 3 topics in battery testing. Characteristics of evaluating of battery cells, voltage, current, temperature testing of fuel cells, and battery leakage. So when you have your battery system in your car, I mentioned this earlier, that's made of various cells. It can be very difficult to measure all the cells separately. Your overall battery system is only as good as the weakest link, which is the weakest cell. Usually one of the cells has issues, dies earlier, or for whatever reason, wears out earlier. And so this is crucial to characterize that to avoid premature failure of your battery or possibly igniting of the whole system. These measurements can be intense depending on how many cells you have. Now, we provide up to 120 channels where you can measure voltage and temperature for each separate cell without having to disconnect the cells from each other. We also get you also can measure temperature at the same time for this module. So with 120 channels, you can have a lot of data that you can acquire in a short amount of time. Voltage measurements can be done in a sampling rate as short as 1 millisecond per sample, depending on what acquisition module you have in your system. Now we offer the system also as a wireless version. So this gives the LR8450-01, allows you to use wireless modules. And again, this is important because you don't always have the access, especially when you're starting measuring data in real time during actual driving conditions. Fuel cells. A lot to be said about fuel cells, but I really want to throw just one thing out there. Fuel cells are, of course, a lot more complicated than batteries. Batteries themselves are complicated enough. Fuel cells add another level of complication to that, which also means that you need to do a lot more measurements. It's not enough to just measure the voltage and the temperature of each cell. Typically, you will have to correlate the state of fuel cell to the humidity. So we need a humidity sensor. That would be for Hioki, that would be a Z2000, for example. And you probably want to measure the current at the same time that goes to your load. So a lot more measurements that have to be done. We have a 8450 that can measure, and I forgot to mention that the fuel cells typically work at higher voltages. The L4050 can accept voltages up to 300 volts directly, so you don't need to have any adaptation. You can hook the 300 volts up directly to the module. Again, up to 120 channels that you can combine as you please. And you can have a humidity sensor at the same time. All the data goes directly into one instrument, so you don't need to have any stitching or any issues with correlation. Now, efficiency has become a major issue, obviously, for electric cars. Right? Efficiency relates directly to range. This is one of the Achilles heels of electric cars these days. The farther you go, the better your electric car is. Leakage current is one of the big problems in batteries. Leakage is any unwanted conductive path in the battery is a leakage current. Leakage current can be measured. Oh, it's actually very difficult to measure leakage current. I mean, you would think you just hook up your multimeter and measure the current that doesn't go through your ports. Well, that's not the case, because what you're really measuring is the characteristics of your multimeter. To measure leakage current or measure low values of leakage current, you need a meter, a voltage meter that has a very high internal impedance, very high internal impedance. Typical multimeters don't meet that requirement. So we built a voltmeter that's specifically designed for leakage current measurement that has a impedance of up to 100 mega ohms, and that's orders of magnitude higher than a regular voltmeter has. The impedance depends, of course, on the voltage range that you apply to the instrument, like any voltmeter. Up to 12 volts, I mentioned that we have 100 mega ohms. Up to 500 volt, we have 10 mega ohms with an uncertainty of plus minus 5%, which is spectacular. So leakage current measurements are not going to be a problem with an instrument like that. So the memory recorder 8741 gives you 16 channels. The MR8740 gives you up to 54 channels. And all of these two instruments are compatible with the voltmeter with these 100 mega ohms impedance. Okay, let me switch on. So we switch gears again. We talked about the mechanical drivetrain, electric drivetrain, combustion engines, specific problems in combustion engines. Let me move towards the digital bus in cars. That's typically a CAN bus or a variation of a CAN bus. I want to highlight two applications or two measurements of the CAN bus. That's non-contactless measurement and then long-term recording of data. The CAN bus, just for references, is a term. The CAN bus is an abbreviation for Controller Area Network. It was invented or introduced by Robert Bosch in 1984, so it's quite old. Has been updated recently to CAN bus FD. FD stands for high speed and variable rate. So a big change there that happened recently with the CAN bus FD. The CAN bus basically measures the various sensors, or connects the various sensors of your vehicle to the control units, the electronic control units. Multiple electronic control units in modern cars, and tens, if not hundreds of sensors. So for example, start-stop button, parking brake, line assistance, they're all connected through a CAN bus to the various ECUs that control the overall system. So it's crucial that this bus works flawlessly. This bus carries all the information about the sensors, the state of sensors, and the control system of your car. Now, the easiest way to attach data or to read the data on a CAN bus is with using a Vicor CAN interface. Our instruments, like the memory recorder 6000, is compatible with the VN1600 family by Vicor. Basically, how this works, you simply take the Vicor CAN bus sensors, hook them up with a USB connector to the memory recorder, and you acquire the CAN data. So this has a few advantages. Number one, you don't take up any of the channels that the memory recorder has, so all the measurements, temperature, strain, stress, ignition timing, whatever you have is still available on the same instrument. So very powerful tool to troubleshoot issues, to design your control system. We support up to 4 CAN channels. We have no restrictions on the number of signals that can be measured that are running on your bus. But we can only display 16 CAN signals at the same time, which is usually plenty. All the data get acquired, of course. Now, one issue, if you don't have access to your CAN bus, one problem is that you need to somehow get the signal into the instrument. Typically, what people doing is to take a pocket knife or of the insulation of the wires and then attach their probes. Now, that obviously is not a good idea. Not to EMI is always an issue. I mentioned this already. Vehicles are very hostile, live in a very hostile environment. You want to avoid EMI, EMC. You have a environment that has high magnetic fields, potential high magnetic fields. So scratching insulation off a cable is not a good idea. Not to mention moisture that can get into the cable and get damage your whole system. What we have built is contactless clips, contactless probes that simply clip onto the wire and can probe the CAN bus through that through these contactless wires. So you don't damage any of the cables. You get your CAN signal into your memory recorder, and it is a non-intrusive way of monitoring your CAN bus. Very powerful tool that's unique in the industry. All right, let's move on from the bus to the ECU. The ECU, the electric computational unit. Now, one of the challenges with the ECU is that just similar to what I mentioned about the measurements of spark signals versus mechanical systems, you have very large differences in measurement signals. So when you're talking about noise measurements or leakage currents, you're talking about ranges of milliamps. When you're talking about starter motors or any electric motors, you might have to measure up to 50 amps at the same time. That is very difficult to do. Typically, what you would have been doing is to use different current probes, one for the other, clip one on, clip the other on, so you cannot measure various signals at the same time. Now, what we do have is a CT6710 that has actually 3 ranges in one probe. So you can measure small currents, you can measure leakage current with a range of 0.5 amps or 500 milliamps the maximum. And you can use the same current probe to measure currents up to 30 amps. So you don't need to change anything. You use the same probe to acquire a variety of signals. Now, talking about ECU, the ECU mentioned acquires the various sensor signals and processes them and controls the state of engine and whatnot. There is a tremendous amount of sensors that are going on in modern cars now. Here's just a list of some of the sensors. They also measure a variety of different physical characteristics. This includes temperatures. This includes an encoder that gives you a speed reading. It's voltages, high voltage up to kilovolts possibly in electric vehicles, to millivolts for leakage current, charging, and of course you need to have calculated values that give you the state of the overall drivetrain, meaning power or various types of powers. That means also that when you start debugging or building a vehicle, that you need to measure a lot of sensors at the same time. Now, what we have is a memory recorder MR8740T that gives you up to 108 channels in one instrument. Sampling rate is up to 20 megasamples per second. So you have enough bandwidth to acquire very high-speed signals. Very important in that context, when you acquire a lot of data, is the size and the form factor of the instrument. Right? So this 8740T is just one instrument that is not very heavy. It's easy to install and easy to use. And again, you don't need to correlate different data from different instruments. All right, let's move on to drive test. Most of the tests I described earlier are done in the lab or in a controlled environment. The proof of the pudding, of course, is in actually driving the vehicle. And a lot of things can happen while you're driving vehicles. Again, you've got a variety of sensor data that you need to correlate to the state of the instrument or the state of the vehicle or to the specific location of the vehicle. And one really cool features that we have with, for example, a memory recorder 8875 is a GPS unit. So we can hook up a GPS receiver, that's a Z5005, that gives you a GPS signal that records GPS data while you're acquiring your voltages, current, torque, temperature, humidity, whatever you're measuring. So it makes it really easy to correlate any unexpected events to the specific location where your car has been at that spin or post stitching of data. You can run that instrument, the MR8875, on battery. The battery pack of the instrument lasts for 1 hour of data acquisition. So it gives you a lot of time to acquire the data that you need when you're out in the field. Now, stress measurement during driving condition, that's kind of the holy grail of real evaluation. With these very stiff car chassis that are being built these days, it's really important to understand what kind of stress-strain relationships you have during actual drives when you hit a pothole or whatnot. How does your drivetrain react to loads going uphill or downhill? And again, a MR88 or memory recorder 8875 gives you the option to include a GPS unit, so you know all the time where you are when you acquire the data. You can use a CAN unit to acquire the CAN data, so you have a overview of all your sensors that are on board of your actual vehicle. And you can attach strain measurement units, the MR8903, that gives you that where you can hook up your strain gauges directly via a bridge box, for example. Now here's another thing that is a step up from there. That is the LR8450-1. That's a wireless unit. So this enables you to use wireless strain sensors that you can put at the various locations of your vehicle and measure strain wirelessly without having any wires connected through the chassis or whatnot into the instrument. Again, so you can, like I'm showing in this plot here on the right-hand side, you can correlate the vehicle speed directly to the state of the strain, state of the stress of your drivetrain or of your suspension system in real time and correlate this without any issues very quickly. All right, so all the tests I described previously were vehicle interior tests or engine tests. Now there is an important part of driver comfort is the interior testing. I mentioned this a few times. We have high magnetic fields in electric cars. It's important that at least you understand what magnetic load you have inside the passenger car. That's easy to do with a magnetic field tester, an FT3470-52, that seamlessly integrates into memory recorders like the 8875. The 8875 gives you a Fourier transfer function. So you can measure your electromagnetic field or your magnetic field with the magnetic field sensor, do a Fourier transform, understand the frequency content of your magnetic field and correlate that to whatever source of the magnetic field you have. Very important measurements that influence driver comfort and compliance ultimately. Our temperature inside a car is very important, it's crucial, right? Temperatures inside cars can get very hot, especially out here in Texas. Summer's coming up. I'm not looking forward to getting in the hot car. What's the impact of a hot car? How is your cooling system working? Do you have an equal or equal heat distribution or temperature distribution in your car? Can the passenger control his or her temperature independently of the driver? How much cross-coupling do you have between the different temperature settings? All these issues are very important for driver comfort. So you're talking about a bunch of sensors that you need to place into your car, a bunch of temperature sensors. It's very useful to use an LR8450-1 that provides you wireless connectivity to a variety of sensors. So for example, you could have up to 210 channels with temperature sensors distributed in your car, and you get a very accurate measurement of all the different locations of your car that you could use for optimizing your heat, your airflow, building better thermal models of the interior of your car, optimizing the windshield, all sort of things that are there. So we provide you the basic measurement tools to do your job better and easier. Again, you don't need to run any wires. Can deploy the system very quickly. Okay, let's move outside of the car and talk about charging. I really have just one slide on that. Charging is a very deep and complicated topic that will determine how well electric cars are accepted by consumers. Again, you've got a bunch of different aspects in electric car chargers. One is that you have a very large range of voltages that you need to monitor. Charging speed is related to the voltage that you can generate, so 1,000 volt or 7,000 volt DC or 700 volt AC is not uncommon in high-speed chargers. At the same time, you do have a CAN bus that controls or that is hooked up to your car possibly, and you have a variety of control signals that make sure that you don't overcharge the batteries, that of course have to do with billing and paying for the charging station. So you have a variety of very different voltages that you need to measure at the same time. And that is our specialty. So memory recorder 8875, for example, can acquire data up to 1,000 volt DC, and you can acquire currents up to 200 amps with a clamp on current probe. And we can provide you logic probes to probe the logic bus at the same time into just one single instrument. Again, we have very high sampling speeds, so we have a large variety, large flexibility in configuring the test system just the way you need to do it. Crash testing, real quickly. Crash testing, especially for electric cars, is a very important evolving field. You have high voltages, you have high batteries, you have combustible material. So measuring the state of your electric system during a crash, while you're doing the crash, is crucial. We do have the tools to do this. Again, an MR8847A is ideal for that, that you can hook up both voltage probes up to 300 volt and 200 megasecond sampling speed. For maintenance, I just have one slide here that I want to run through real quickly. I mentioned the CAN bus probes, the contactless CAN bus probes already. So we have contactless probes that give you voltage signals without the need to pierce insulation of a cable that's crucial for the long-term viability of your car. And I mentioned moisture that gets into cables, you pierce them. So really you want to have uninvasive testing, non-invasive testing during maintenance. So let me summarize real quick. Modern vehicles, I hope I showed you that there's a variety of, it's a staggering variety of tests, that electric tests, electromechanical tests that you need to do in the lab, in the development lab, as well as in the field while driving. It requires specialized equipment. The equipment needs to be small and portable, and you cannot load up your car with a bunch of equipment that would possibly change the driving characteristics of your car. It typically requires a massive amount of channels that you need to acquire at the same time with high sampling rates. And measurements have to be done at vastly different time scales. We provide these tools for you. And I want to encourage you to contact us if you want to. We are located in Plano, Texas. That's in the DFW Metroplex. We just moved there a few months ago from New Jersey. We have a very active YouTube channel with a variety of demonstrations of our instruments. You can always call us by phone and or check us out on our website. With this, I want to thank you for your attention and pass the word back to Jennifer. Jennifer?
Yes, thank you so much, Chris. Now, I guess we can move on to our Q&A session. And now Michi and Yagi will go ahead and answer some of the questions that you guys have asked. Now, are you ready?
Hi, I'm ready. Okay, so let's begin with the opening question. First question is basically how the phase shift function of the PW6001 works. So I'm afraid I cannot say much of a principle of the function, but this one is our proprietary technologies, and our phase shift functions results were compared using standard equipment, standard calculator. So the test results, output results are output results of the PW6001 is very close to the output of the standard calculator. And if we are using this function, we need to input a unique phase shift point on the meter manually. So each sensor has a unique calibration point. So once you input a certain value on the meter, you can use these settings with different but the same type of sensors. So this function is only this function can only works with Hioki current sensors. This function does not work with different brands. So this is a bit notice. And the second question is so how the Hioki memory recorder can start recording or to find fault conditions by triggering. So the Hioki memory recorders have triggering functions So so you can set the level triggers, and you can set the window trigger and other trigger. So once you set the trigger, then start recording. At a certain point, the meter is triggered and recording starts. This kind of process, the memory recorders go through, so we can find out which at which point fault occurs. Okay. Okay. So other question I got is, what is the difference between oscilloscopes and Hioki memory recorders? So basically, memory recorders a lot of difference from oscilloscopes. So one is all channels are isolated. So you can use the memory recorders at the different power system to be connected. So, and eliminate common mode noise issues. And also memory recorders allow you to use different types of measurement module. You can do direct input of high voltage like 1000 volts. And also you can do current measurement as well. And the other different point is the memory recorder has high data storage capacity. So you can, oscilloscopes are designed for instantaneous signal measurement, but the memory recorders can do monitor signals for a longer period of time. So memory recorder has a lower sampling rate, but high vertical resolution, 16-bit or 24-bit, something like that. You can detect. You can see very tiny signal change on the meter. All right, I think that's all I've got. Thank you.
All right, thank you. Now, we hope everyone enjoyed this webinar. We really appreciate you taking out the time to attend. There is a short survey right after the webinar, so please don't close out your window, and if you can just give us your honest feedback, that will be really helpful for us to host another intuitive and informative webinar. Thank you so much, everyone. We look forward to seeing you on our next webinar sessions. Thank you very much. Thank you, Chris. Thank you, Nao-san. Thank you, Yagi.
Thank you.
Hey, Chris.
Hi, people still there?
Yeah, here. I think Chris left.
You gather them for a little debriefing later on.
I will.
Okay.
Okay, I'll call you with them. All right.
All right.
Bye.
Thanks. Bye.
Thank you, guys. Bye.
Thank you.